Okay, all right, we'll go ahead and get started. This is week 7 Friday. Can you believe it? It's already, we're at the end of 7th week, 70% done. This is, I just know, so my entire educational career has been on the quarter system, and so I know the pacing, and I know 7th week is when, like during the first 6 weeks, you're kind of juggling and trying to keep everything afloat, and 7th week is when the things start to go a little off kilter, and it's hard. It's hard to stay afloat, especially when it's like second round of midterms, things like that. Anyway, always the plus side was it's all going to be over in a month, okay? And we'll get there. We'll get through it, and you guys will get through it. Okay, so we are continuing on. I've got a couple more root finding methods to talk about today. And then after I finish out those root finding methods, then I will start talking about optimization, okay? And what we'll see is how we can start off with the simple idea of trying to find the location where a function equals 0, and how we can use that to then build on that to then try to optimize a function. Optimize meaning finding the minimum or the maximum. Well, I guess generally a local min or a local max. And all of that plays important roles in what we can do in kind of statistics and things like that. So, all right, 2 hours to a full charge, that's fine. All right, so we left off on Wednesday. We talked about the Newton-Rapson method for finding a root, okay? So I'll say last time we had Newton-Rapson, and the idea of Newton-Rapson, oops, so here's our root, is, you can find tangent lines, okay? So we go there, we find a tangent line, we go there, we find a tangent line, so on and so forth, okay? Until we approach the root that we're looking for. One drawback of the Newton-Rapson method is that we need to be able to find the derivative of the function. In order to figure out the slope of the tangent line, we need to be able to find the derivative, and in some cases, we either don't know the derivative, or we can't figure out the derivative, or something, right? So Newton-Rapson requires, now we find the derivative. Okay, so there's another method, all right, that avoids derivatives, that's similar to Newton-Rapson, but it's called the secant method, secant line, okay? So secant line is basically just 2 points on a curve, and you connect them. And it's similar to Newton-Rapson without the derivatives. Okay. Now, what we require now is we require 2 starting points of x. Okay, so we'll call those x0 and x1. Okay, and so the picture here, I'll go ahead and just kind of maximize this, is so this will be our x-axis. This is y equals 0, and I've got some kind of curve here. And here, it doesn't matter. One of these, maybe I'll call this one. This one will be x0. This is x1. And what we do is we connect these two lines with the secant line. Right. So that a straight line passes through here. So this is supposed to be straight. It's hard to draw, okay? Okay, so this is our secant line. Secant line connects, so connects the points. What are the 2 points? Yeah, so it'll connect kind of the points x0 and f of x0 and x1 and f of x1, okay? So it connects those 2 points and continues down to the x-axis. Down, or up. I'll just say continues to x-axis, and where it intersects the x-axis will be the next value of x. So we follow that, and then so this location right here becomes x2. And we come up to here at x2, and then I guess I'll draw another secant line. So now I'm going to use x, kind of these 2 points, and draw. It's hard to draw a straight line here, okay? And we draw a secant line there, and then this will become x3, and so on and so forth, okay? And then you'll use this point, and so on like that. Is that okay? All right. So let's figure out if we have x0 and we have x1, where is x2? Okay. So we have x0, f of x0, x1, and f of x1. Okay. Okay, where is x2? Okay, so what we're going to do is, let me just kind of, we'll zoom in on this triangle here. Okay, so I'm going to just, so we've got some curve, it doesn't matter, okay? And we're gonna see. I have the straight line tool, but it like keeps you can't whatever. Okay, I'll try it. It like locks on the grid. I'm just gonna freehand it. All right. Okay, so I'm going to just try to draw a triangle here, okay? That looks okay. All right, so what we can do is we can kind of split our triangle up like this, okay? And we have these 2 locations. We know this one is x0 and f of x0. And we know this spot is x1 and f of x1. Okay, and what we want to know is where do we end up here? Okay, where is this location? So what we'll what we have here is we're going to call this triangle. We're going to take a look at this triangle. And we're going to say this is the rise, this leg here. This will be our run. And so we have x2 is equal to x1 minus the run, okay? And so much like before, we can say slope is equal to rise over run. And so we'll say run is equal to the rise divided by the slope, okay? All right, now, how do we figure out the slope? Okay, so I'm going to just rewrite this. So run is going to equal to rise times inverse slope, okay? And we know the rise is equal to f of x1. Is that okay? And so now the last thing we need is we need the slope, which we'll come and look at this other triangle, all right? So we need to know the slope of this line, which is going to equal kind of this rise divided by this run, okay? So this, I'm going to write in red. This will be rise over run. Maybe I'll call this rise prime, and I don't know what to call it. Okay. All right. So so over here I've got I'm going to do run over rise because it's inverse, right? So the run is equal to what?
x0 minus.
Yeah, x0 minus x1, or we'll go left to right. So we'll go x1 minus x0, and then the rise will be the difference between f of x, I guess it doesn't matter, f of x1 minus f of x0, okay? Yeah, I guess I can do, in our picture it makes sense to go 0 minus 1. So I'll just do it that way. It doesn't matter. As long as you're consistent, it'll be fine, okay? So our run is the kind of the length of this base, and then the rise is how tall it is, and that's going to be the difference between the x0s and the difference between the fx's, okay? So we combine all of that together, and we're going to say x2 is equal to x1 minus f of x1 times the run over the rise. x0 minus x1 divided by f of x0 minus f of x1. Okay. And, you know, if we did x1 minus x0 and f of x1 minus f of x0 would be the same. So it doesn't matter which one you do. Okay. Does that make sense? Okay. And so that will give us the location of x2, right? So the picture is this, okay? Of course, the computer doesn't actually draw these pictures or anything. So we're going to say our next iteration is going to be this, and then so in general, the next value, xn plus 1, is going to equal xn minus f of xn times, and again, I'm going to kind of swap the letters around just to meet the, I think this is how the book has it written, xn minus 1 divided by f of xn minus f of xn minus 1. And that's it. So no derivative is required for this method. It just you just need two starting points, and your current and then a previous one, an xn and an xn minus 1. Okay. And can be done like that. Okay. I think I have you guys code this up in your homework as well. Okay. And I think with the other examples we've done, it's a good exercise there. All right. Any questions here? Okay. All right. And then lastly, we have bisection method for root finding. Okay. And Newton-Rapson method and secant method and fixed point, none of those are guaranteed to work. The bisection method is the only method that's guaranteed to work if your function is continuous between kind of your boundaries. Okay, so this is the only method guaranteed to work for continuous f of x. Okay, and the idea is simple. All right. Basically, you have a left boundary which we'll call xl1, and a right boundary which I will call xr1. Okay, so this is left boundary and right boundary at time 1. Okay, and the only requirement is f of the left boundary must have the opposite sign of f at the right boundary. Okay, and so if you have opposite signs on the left and right, there has to be at least one root between the left and the right. Okay. Okay. Now, like all of these other computational methods, depending on your starting point, it might converge to different locations, different solutions. And so this was guaranteed to find kind of at least one of the roots. Well, as long as I guess yeah. So okay, so here's our picture. So we've got some kind of function here, right? Okay, and so I might call this xl1, and right here will be xr1. Just get rid of this line here. Okay, and so f at xl1 is down here, and f at xr1 is up here. And all we do is we just find the halfway point between xl1 and xr1. So we'll call this xm1, the midway point, okay? And then we calculate the value of this halfway point. So xm1, so find halfway location, which will be xm1 is equal to xl1 plus xr divided by 2, okay? And then find f of x m1, okay? And then what you do is whatever this sign is, you keep the you'll use xm1 and you'll keep the other one that has the opposite sign. Okay, so for the next iteration, keep xm1 and either xl1 or xr1 choosing the one with the opposite sign. Okay, so with that, if we do that on our next iteration, this becomes xr2, and this will become xl2. Okay, so we'll keep xl1. It becomes the left end for our second iteration, and we'll keep xm1, and it becomes the right end for our iteration. Okay, and then we find the halfway point here. We'll call this xm2, and it becomes right there. And so with this one, we are going to keep xr2. Let me so this will become xr3, and this one will become xl3. Okay, so we have our left bound and our right bound, and then we split that in half, and this will become x midpoint 3, and then we have to decide whether to keep the left one or the right one, and we just continue to do this back and forth, okay? Keep splitting it in half over and over and over again, and keeping the two endpoints that have opposite signs, okay? So of the three things there, okay? And that's it, okay? And just keep going until basically xln minus xrn is less than some tolerance level. So the only drawback of this is that it converges. It usually takes more iterations to reach your desired convergence level, whereas the Newton-Rapson method, if it works, it generally converges very quickly. With the bisection method, you're splitting everything in half, and so kind of that distance, that the distance between the endpoints keeps shrinking in half, which is pretty good, but you know, some of the other methods go faster. Okay, but this one's guaranteed to work. Okay, just because of math rules, right? So, so as long as you have a continuous f, there's guaranteed to be a route between these two endpoints. Okay, are there any questions? Yes.
In the Newton-Rapson method, when you take a tangent line, what if the tangent line goes past the root and then intersects past the root? Is that okay?
Well, so all the lines, any line you draw, right, continues on to negative infinity and positive infinity. Okay, and so all you do is you just pick it where it intersects the x-axis. And so with Newton-Rapson method, yeah, you might start over here. The tangent line shoots you, and then the root is like right here. And the tangent line shoots you past it, but you just keep going, and you'll find the tangent line at your new location, and it will, because the rule is follow the tangent line until it hits the x-axis, it will generally get you closer to where the function intersects the x-axis. Okay. But again, there's some weird things where you can end up in the infinite loop. You can end up at a location where the tangent line is practically parallel to the x-axis, and then it fails. Things like that. So yeah. So the different methods have drawbacks. Okay. You know, even using calculus and algebra, which is generally the quote the best method, the analytic method, that has drawbacks in that it's hard. So so anyway, these computational methods are very handy. Okay. All right. So that's it for root finding methods. Is this okay? All right. And so I mean, you know, finding roots in of itself can be a useful thing, but a lot of times we're more often interested in optimizing a function. Okay. So we're going to start talking unidimensional optimization, okay? Just meaning you have a function of one variable and we want to find the local minimum or local maximum, okay? So, you know, just so a few examples of this, which will be important. So, how does linear regression work? Just statistical applications of optimization, okay? All right, so recall ordinary least squares. Ordinary least squares regression. Okay. OLS regression. Okay. The coefficients B0 and B1. Okay, and y equals b0 plus b1. Let's say y sub I is equal to b0 plus b1 x sub I plus e sub I. This, how are the coefficients b0 and b1 chosen? Are chosen so that somebody's got to know this, right? You guys are in 101A right now? Okay. This should have been covered like week 1. Okay. So that what? yi minus yi hat squared across all i's is minimized. Right? So basically we're trying to minimize the sum of squared residuals, sum of squared error or residuals. Okay, so that's one thing, right? You've got this function. What do you call this function anyway? This sum of squares error. Well, all right. Well, does the term loss function, does that sound familiar? Okay, well, all right. 102b, we'll talk about loss functions. Okay, so basically this is a measure of how good this line is, right? If this value yi minus yi hat is big, then the line did a bad job of estimating that value, okay? But if yi and yi hat are very close together, then that means the line did a pretty good job. And so what we want to do is we want this to be as small as possible because this is a measure of how good or bad our line did, okay? This thing being huge would mean our line did bad. If another line has a smaller thing, we've got a better line, okay? And so we choose B0 and B1 in such a way that this thing is minimized. Now, this is not unidimensional optimization because how many things are we adjusting? 2. We're adjusting B0 and B1. We're trying to find the best intercept and the best slope, okay? And because we have 2 parameters to adjust, it's not a unidimensional problem, okay? But it's still an optimization problem, okay? It's still an optimization problem. Now this has been solved. People did calculus, and they said, okay, B1 is going to be R times S of y divided by S of x, and B0 is going to be y bar minus x bar times B1, and things like that. And that is the calculus derived optimal solution for the line of best fit, right? Assuming that your errors follow a normal distribution, things like that. But it's still an optimization problem. We're trying to just minimize this sum of squared residuals, okay? This is a function of 2 variables, B0 and B1, okay? All right, what about maximum likelihood estimation? So you should be, not everyone is, but you should be enrolled in 100B right now, or you've taken that already. And you should have covered maximum likelihood estimation there. And so what are we trying to do in maximum likelihood estimation?
Try to find parameters and maximize likelihood.
Yes, okay. So we are trying to estimate the parameters of some probabilistic process, okay? So you have a probability process, so maybe it's like flipping a coin and you want to figure out what is the proportion that this coin lands heads based on the observed data that I have, right? Or if I'm randomly drawing values out of the population, what is the mean of that population, okay? That we're trying to estimate the mean of that population. So we're saying based on the data I've seen, and I'm imagining that there's this probability process where basically my values are coming from the normal distribution centered at some unknown parameter, the mean of the population. What we want to do is we want to figure out what's the best value of the mean to use so that the likelihood of my data is maximized, okay? Another optimization process, okay? So here, maximum likelihood estimation is we want to find the value of some unknown parameter of the population so that the likelihood of observing the data that I have right now, the data that I've already observed, is maximized. Okay. So, you know, for example, like we may imagine x comes from a normal distribution centered at mu with standard deviation equal to, I don't know, 10, right? So this is our data. This is our unknown mean, okay? And then we'll say x is equal to, you know, we get 100 and 120 and 90 and 80 and 105 or something like that, okay? What does this average out to be? A mean of 99, I think. Okay, x bar is equal to 99 or something like that. So the what we want is we want to know what value of mu will maximize the likelihood of observing this data, right? So the likelihood, what is the likelihood of our data? Likelihood of data, assuming all observations are independent, that's going to just be the probability of getting x equal to 100 times the probability of getting x equal to 120 times the probability, et cetera, right? So this just ends up being the product of the probabilities of x being each value, given that they come from this distribution, okay? And we're basically, if somebody said, oh, the mean of the population is 200, you'd say, no, that can't be right, because I kept getting values like 100 and 80 and 90 and things like that. And if the mean of the population was 200, then these values are practically impossible. I have a very, very low likelihood of this data, right? If somebody else comes along and says, I think the mean of the population is 120, you'd say, I guess that's possible, but it's still pretty unlikely that I would get values like 80, okay? Whereas somebody comes along and says, I think the mean of the population is 100, or the mean of the population is 99, those are a lot more compelling because that seems to make sense with the data we've seen. And maximum likelihood estimation just says, well, I've got an exact formula, I've got an exact equation for the likelihood of my data. Why don't we just try to maximize it, okay? So what value of mu will maximize this likelihood, okay? Is that okay? So that's maximum likelihood estimation. And when you have a product and you're doing this like the calculus way, like it's really hard to take a derivative of a product. So what's the trick we employ? We take the log, we turn the product into a sum. It's a lot easier to take derivatives of a sum than a product, okay? And because the log function is monotonic, if the function maximizes the log, if a value maximizes the log of a function, it's going to be the same value that maximizes the original function, which is nice, right? Okay, so anyway, that's what we've got. So these are just a few applications of optimization, just a side detour. And so let's just talk about, in calculus, how do you find the local minimum or local maximum of a function? What do you do? Take the derivative of the function and you set it equal to 0, right? And that's exactly our strategy for us, okay? We have root finding methods that says, oh, I know how to find the 0. I know how to find where the function is equal to 0. So practically all of our root finding methods can turn into optimization methods by just applying the root finding method to the derivative of the function, okay? So all of our root finding methods okay, so let me just write. We do the same thing. Okay, all of our root finding methods become optimization methods when we apply them to the derivative of a function. Okay. So right now, all of the kind of the methods that we've learned earlier, they are good at finding where our functions equal 0. And all we have to do is we just take our original function, we take the derivative of that, and apply a root finding method to that, okay? So let's say, what's that?
How do you take a derivative in R? Do you do it manually?
Yeah, you have to do, so in the beginning you have to do a little bit of calculus. You have to find the derivative of the original function, right? So it feels like it defeats the purpose, but so there's a few things we can do, but yeah, so we just have to take the derivative. Now, if we can't take the derivative, we have other methods in our back pocket too, okay? So if we want to optimize a function g of x, okay, we take the derivative, okay, and we let f of x equal g prime of x, okay, apply a root finding method to f of x, okay, and the roots of f of x will be critical points of g of x, okay, and then we can choose or we can select whichever one, select the ones that are local min or local max. Okay, so yes, this assumes we can take the derivative of g of x to get g prime of x, okay? So okay, so just a quick example. Quick example of converting Newton-Rapson for optimization. Okay. So Newton-Rapson for root finding, for finding the root of f of x, worked like this. xn plus 1 is equal to xn minus the run, which was f of xn divided by f prime of xn. Okay, so this is just off to the side there. So we'll say Newton-Rapson for optimizing g of x, okay? So we'll let f of x equal to g prime of x, okay? And then f prime of x will equal g double prime of x, okay? So this requires g of x to be twice differentiable. All right, and if it's not, then this method's not going to work. Okay, so we have the same algorithm. So if f of x is equal to g prime of x and f prime of x is equal to g double prime of x, then we find the roots of f of x. xn plus 1 is equal to xn minus f of xn divided by f prime of xn. This will give us find roots of f of x, which are equal to critical points of g of x. Okay, and so this just becomes, if I just replace everything else, I can just deal directly with the first and second derivatives of g of x, and I'll have g prime of x divided by g double prime of x. Okay. We'll find critical points of g of x. And that's that, okay? So if you take any of our root finding methods and you apply it to the derivative of a function, it'll find local mins and local maxes of that function, okay? Which is quite handy because we've got several applications on which we want to find minimums and maximums. Okay, have a great weekend, you guys. We'll see you on Monday.